In exercise number 1, let A is equal, so we have this matrix. This is, and the transformation T is from R2 to R2, defined by Tx is equal Ax. Find the image under T of U and V. So we want to find the first one is Tu. That's mean we need to find AU. So we take the matrix A, we multiply it by the vector U. So here A, this is U1 minus 3. So now we do the multiplication. 2 multiplied by 1, 2 plus 0. So this one 2. 0 multiplied by 1 plus 2 multiplied minus 3. This one is minus 6. So this is TU. Now to find TV, so this is just AV. So A is 2, 0, and here we have 0, 2. We multiplied by V, which is AP. This will give us 2 multiplied by A plus 0. So this is 2A. 0 multiplied by A plus 2 multiplied by B. This one is 2B. So this type of transformation is called shear transformation. In exercise 3 and 5, so from 3 to 6, with T defined by Tx is equal Ax, find a vector x whose image under T is B and determine whether x is unique. So here we have a matrix A and we have the vector B. We ask to find the vector x such that Ax is equal B. So we need to solve this matrix. Here we have 1, minus 2, 3, 0, 1, minus 2, minus 2, 6, minus 5, and our B is minus 1, 7, minus 3. We want to do row operation for this matrix and see what is the x of this system. If the system is consistent without any free variable, that means x is unique. But in case we have a free variable, that means the system has infinitely many solutions. So after doing row operation for this matrix, we get the final result, this one. So from here, our x is equal, we have 3 variables, so x1, x2, x3. So our x is equal, x1 is equal 3, x2 is equal 1, x3 is equal 2. So since we don't have any free variable, we have only all the variables are basics. That means x is unique. So there is no more than one x because there is no free variable. Similarly, in 5, we are given the matrix A and we are given the vector B. We need to find the vector x whose image under T is B, and we need to determine if x is unique. So also we'll do row operation for this matrix and see if x is unique or it has many solutions. So after row operation we get this matrix. So from here it is clear that x1 is equal minus 3, x3 plus 3, x2 is equal minus 2, x3 plus 1, and x3 is equal to x3. That's meaning x3 is a free variable. So when x3 is equal to 0, our x will be equal. So if x3 is equal to 0, x1 will be equal 3, x2 will be equal 1, and we choose x3 to be 0. Here determine whether x is unique. Since here we have x3 is a free variable, so x is not unique. X is not unique because we can choose x3 to be any value. So this is when x3 is equal to 0. If we have x3 is equal 1, we have another vector x. If x3 is equal to, we have another vector x. So x is not unique since x3 is a free variable. In 7, let A be a 6 by 5 matrix. What must A and B be in order to define T from Ra to Rp by Tx is equal Ax? We know that the transformation take the vectors from Rn to the vector Rm. So since a matrix A is 6 by 5, that's mean إنه M is equal 6, N is equal 5. So from here the transformation T should be from Rn, so from R5 to Rm, which is R6. So A will be equal 5 and B will be equal 6. For 8, how many rows and columns must a matrix A have in order to define a mapping from R4? So the mapping here we have T from R4 into R5 by the rule Tx is equal Ax. So this is, here we have from R4 to R5. We know that R4 to R5, that's mean from Rn to Rm. So the matrix A, we know that it is M by N. So our A should be from, it has 4 columns, 5 rows, so it will be 5 by 4 from this one. This one is M. So our matrix should be 5 by 4. In exercise 9, find all x in R4 that are mapped into the 0 vector by the transformation xAx for the given matrix A. So here we are looking for the vector x, that is when we multiply it by A we get the vector 0. So here we have Ax is equal the 0 vector. We are given the matrix A, we are looking for the vector x, that's when we multiply it by A we get the vector 0. So we'll do row operation for the matrix A 0, which is our B will be 0, and we are looking for the x. So our row operation leads to this matrix. From here it is clear that x1 will be equal, so x1 will be equal 9. If we say this one is x1, x2, x3, x4. So x1 will be equal 9 x3 minus 7 x4. x2 will be equal 4 x3 minus 3 x4, and x3 is a free variable, so this will be equal x3. x4 also a free variable, so this will be equal x4. Now if we write it as a vector, so this will give, if we take, so we have 2 free variables, so this will be equal, if we say x3, so this is our x is equal, if we say x3 and we take the factor of x3 from the first one, second one, third one, fourth one, so 9, then 4, 1, 0, plus another free variable which is x4, the factor of, or the coefficients of x4 is minus 7, 3, 0, 1. So we have more than one x when we multiplied by the vector, when we multiplied by the matrix A we get the vector 0. So if you choose, for example, x3 to be 0, x4 will be 1, you will get the vector minus 7, 3, 0, 1. If you choose this one, x3 to be 1, x4 is equal to 0, so you get the vector 9, 4, 1, 0. So there are infinitely many solutions of this matrix. Let B is equal minus 1, 1, 0, and let A be the matrix in exercise 9. Is B in the range of the linear transformation xAx, y, or y not? So we are looking for a solution of the matrix AB. If this matrix is consistent, that means B will be in the range of the matrix A. But if the system is inconsistent, that means B is not in the range of the matrix, or not in the range of the linear transformation. So we'll do row operation for the matrix AB, and we see if B is in the range or not. So doing row operation for the matrix AB, we get this last form of the equation. Since this one is clear, it is consistent. Here we have a leading entry. Here we have a free variable. So we have two free variables. This system is consistent, and we say that yes, B is in the range of the linear transformation. So we said yes, since the system is consistent. In exercises 13 to 16, use a rectangular coordinate system to plot U, which is 5, 2, V minus 2, 4, and their images under the given transformation T. Make separate and reasonable large sketch for each exercise. Describe geometrically what T does to each vector x in R2. So here we have the transformation Tx. This is our matrix, and this is the vector x1, x2. We need to know when we multiply or when we find Tx of the vector uv, what happened to this vector. We need to sketch this one geometrically. So for 13 first, we will find what is Tu and what is Tv. From here, it is clear if we have, for example, x1 and x2. So minus 1 multiplied by x1 plus 0 multiplied by x2. This will give us minus x1. Then 0 multiplied by x1 plus minus x2. So this is minus x2. So if we have a vector x1, x2, after the transformation, the result will be minus x1 minus x2. So if we have now the vector u, 5, 2, under the transformation, tu will be equal minus 5 minus 2, because we get it from this one. If we have in general way x1, x2, under the transformation, it will be minus x1 minus x2. Now our x1 is 5, our x2 is 2. So Tu will be equal minus 5 minus 2. Similarly, Tv will be equal, our V is minus 2, 4. So Tv will be minus minus 2, which is 2, and minus 4. Now we need to sketch U and V, and also we need to sketch Tu and Tv to know what happened to these vectors under the transformation. So first we sketch the vector u, which is 5, 2, and we sketch also the vector v, which is minus 2, 4. So after the transformation, tu is minus 5 minus 2, which is this one, and tv is 2 minus 4, which is this one. So now we see that after the transformation from u to tu and from v to tv, this is just a reflection through the origin. So this is a reflection through the origin. يعني راح يصير انعكاس اللي هو الفيكتور حول اللي هي نقطة الأصل الأوريجين 0 0. We'll do the same way for 15. So here our tx is equal 0 0 0 1, and we have x1 x2. So if we multiply 0 by x1 plus 0 by x2, this will give us 0. 0 by x1 plus 1 multiplied by x2, this will give us x2. So now we need to know the reflection, or sorry, we need to know the transformation of the vector u. So tu will be equal x1 will be 0, x2 will be 2. Similarly, we need to know what is TV. So TV will be 0 and x2, which is 4. So now we need to sketch this one, u and v, and also we need to sketch tu and tv and see what is the geometric description of this one. So this is our u, which is 5, 2, and this is our v, which is minus 2, 4. After the transformation, tu is 0, 2, which is this one, tu, and tv is 0, 4, which is this one. So we say that after the transformation, we project every vector into the x2 axis. So we said that the geometric description is a projection onto the x2 axis. يعني نشيل كل فيكتور ونخليه في ال x2 axis لأنه قيمة ال x1 is equal to 0 تبقى لنا فقط قيمة ال x2. So this is a projection onto the x2 axis. Let T be R2 to R2 be a linear transformation that maps U5 2 into 2 1 and maps V1 3 into minus 1 3. Use the fact that T is a linear transformation to find the images under T of 3U 2V and 3U plus 2V. So we are given that Tu is equal to 1. Also, we are given that TV is equal minus 1, 3, because this is the mapping of 5, 2, and the result will be 2, 1. The mapping of 1, 3, the result will be minus 1, 3. Now we need to use the fact that T is a linear to find what is the transformation of 3U. So now the transformation of 3U, so T 3U, we know that the transformation is linear, so we can take 3 out, so it will be 3Tu. What is Tu? It is given here to 1, so this is 3 multiplied by 2, 1. This will give us 3 multiplied by 2, 6, 3 multiplied by 1, 3. Also, we need to find the transformation of 2V, so T 2V will be equal to TV since the transformation is linear. So what is TV? It is given minus 1, 3. So the result will be minus 2 and 6. Also, we need to find the transformation of 3U plus 2V. So this is T of 3U plus 2V. This will give us T of 3U plus T of 2V. We said that the transformation of 3U it is 6, 2, so we use the previous result, plus the transformation of 2V is minus 2, 6. So this will give us 6 minus 2 is 4, 2 plus 6 is 8. Sorry, this one is 6, 3, not 6, 2. So here, this one 3, and this one will be 9. 3 plus 6 will be 9. Let E1 is equal 1, 0, E2 is equal 0, 1, Y1, 2, 5, Y2 minus 1, 6. And let T to be from R2 to R2 be a linear transformation that maps E1 into Y1. So from here we know that T E1 will be equal Y1 and maps E2 into Y2. So T E2 is equal Y2. Find the images of 5 minus 3 and x1, x2. So now we need to find what is T5 minus 3. So we need to find this one, sorry, 5 minus 3. We need to find the image of this one. So this will be equal to, we know that the transformation, so here we have the transformation AX will be equal T E1 T E2. So now here we have T 5 minus 3, so this will give us T 5 E1 plus minus 3 E2. So this will give us 5, since the transformation is linear, so 5 T E1 minus 3 T E2. So what is T E1? T E1, it is given that it is equal Y1, which is 2, 5 minus 3. What is T E2? It is given that Y2, which is minus 1 and 6. So now this will give us 10, 25 minus 3, 80. So the result will be 13, 7. So this is the transformation of the vector 5 minus 3 under the mapping from R2 to R2. Also we need to find what is T x1 x2. We'll do in the same way. So T x1 x2 this will be equal T x1 e1 plus x2 e2. So this will be x1 T e1 plus x2 T e2. This will give us x1 T e1, it is just y1, which is 2, 5 plus T e2, it is y2, which is minus 1, 6. So the result will be 2x1 minus x2 and 5x1 plus 6x2. So let x is equal x1, x2, v1 is equal minus 2, 5, v2 is equal 7 minus 3. And let t be transformation from R2 to R2 be a linear transformation that maps x into x1 v1 plus x2 v2. Find a matrix A such that Tx is Ax for each x. So we know that the transformation is x to Tx. That means it is equal, it is given here, x1 v1 x1 v1 plus x2 v2. We know this one can be written like v1 v2 multiplied by x1 x2. We are looking for the matrix A. So that means this is our A. We can represent it as Ax. So from here A will be equal v1 v2, which is equal v1 is minus 2, 5 and v2 it is 7 minus 3. So this is our matrix of transformation. In exercises 21 and 22, mark each statement true or false to justify each answer. So the first one, a linear transformation is a special type of a function. The function, if we have a function, we have to plug in something in this function and we get a new thing. Similarly, in the linear transformation, we have a mapping. We put some function or we put some function, vector in this transformation, we get another shape of this. vector. So this one do it the same way, so this one will be true. True statement. Now B, if A is a 3 by 5 matrix and T is a transformation defined by Tx is equal Ax, then the domain of T is R3. We said that the domain is always in Rn, but here R3 is not Rn, R3 is Rm. Sorry, R3 is not Rn, it is Rm. So this one should be false. The domain of T will be all the vectors is in R5. C, if A is an m by n matrix, then the range of the transformation Ax is Rm. We say that the range is the set of all image or the set of all linear combination of the columns of A. So this one should be false. The range is the set of all linear combination of columns of A. Sorry for this mistake. So here of columns, or we can say the set of all image of the transformation. D, if every linear transformation is a matrix transformation, we say this one is false. It could be this one, we can write it as every matrix transformation is a linear transformation, but not every linear transformation is a matrix transformation. E, a transformation T is a linear if and only if TC1V1 plus C2VT is written by C1TV1 plus C2TV2 for all V1 and V2 in the domain of T and for all scalars C1, C2. This one is true. It is from under it. You will find it after in the textbook after the definition of a linear transformation, which was the statement IV. So now 22, every matrix transformation is a linear transformation. We said this one is true. B, the codomain of the transformation X, Ax is the set of all linear combinations of the columns of A. We said this one is not the codomain because the codomain is Rm. So this one is false. This is not the codomain, it is the range. Now C, if T is Rn to Rm is a linear transformation, and if C is in Rm, then a uniqueness question is C in the range of T? No, this is not a uniqueness. It should be, this is the existence. So this one is existence. Because if we ask if C in the range, so this is the existence. If we said is C is the only vector who maps are in who we can maps in from Rn to Rm, this is also okay, uniqueness. But here we said is C in the range of T, that means this is the existence, not uniqueness. D, a linear transformation preserves the operations of vector addition and scalar multiplication. This one, it is clear true. We see here TC1V1 plus C2V2. This is C1TV1 plus C2TV2. There is no change in addition or multiplication of the or scalar multiplication of the vectors. Now E, the superposition principle is a physical description of a linear transformation. This one is true, and we have seen that T0 is equal 0. In 26, let U and V be linearly independent vectors in R3, and let P be the plane through U, V, and 0. The parametric equation of P is X is equal SU plus TV with ST in R. Show that a linear transformation T from R3 to R3 maps B onto a plane through 0, or a plane onto a line, or into a line through 0, or onto just the origin in R3. What must be true about TU and TV in order for the image of the plane P to be a plane? So it is given that any point X in the plane B satisfy this equation. X is equal, it is given SU plus TV. And we know that the transformation is a linear transformation. So if we do the transformation here, T of X will be equal T SU plus TV, which is equal S TU plus T TV. So now this transformation is a linear transformation, and the set of image will be the span of TU and span of TU and TV. So we can write here the set of image is just span TU TV. So now we need to discuss that or show that the linear transformation map a plane into 0, or into a line through 0, or just into the origin. So according to this, we see that the image is span TU and TV. So the result will be just in span TU and TV. So what are the case of TU and TV that makes our plane just be a plane through 0, or a line through 0, or just through the origin? So if the relation, if we can distribute this in 3 parts. So the first one, if TU and TV linearly independent, so that means there is no relation between TU and TV. The result will be, so the span TU TV will be the plane. Will be a plane through TU, TV and 0. So if TU and TV are linearly independent, the span of TU, TV will be a plane through TU, TV and 0. Now if TU and TV linearly dependent, what happens to the plane? So if TU and TV linearly dependent, and not both of them 0, so one of them just only 0, so and not both of them 0, span TU TV will be a line through the 0 point and the vector. So here span TU TV will be a line through 0. Now for the case where TU and TV, both of them is equal to 0. So now if TU is equal TV, TU is equal TV, both of them will be equal 0. So the span will be span 0 will be just a point through the origin. So this is will be onto the origin. So here we have three cases. We are given that for any point in x the plane B satisfy this in the plane B satisfy this. يعني هو معطيني اللي هي أنهي نقطة في البلين تحقق المعادلة هذه. فالحين نريدني أشوف بعد الترانسفورميشن. We need to show that إنه بعد الترانسفورميشن النتيجة راح تصير يا أنها تكون a line أو إنها تكون a plane أو إنها تكون إيش a point. فنحن سوينا الترانسفورميشن. لاحظنا من الترانسفورميشن just we have two vectors اللي هم t و tv. إذا الأول الإيمج عبارة عن إيش؟ عبارة عن سبان tu و tv. فالحين ناخذ الكيس of t و tv. إذا كانوا linearly independent إذا السبان راح تصير بلين. إذا كانوا linearly dependent واحد منهم يساوي 0 إذا راح تصير line through 0. إذا كانوا باثنيناتهم يساوي 0 إذا راح يصير عندي point through the origin. In 30, an affine transformation T from Rn to Rm has the form Tx is equal Ax plus b, with A an M by N matrix and B in Rm. Show that T is not a linear transformation when B is not equal to 0. Affine transformations are important in computer graphics. So here we have the transformation Tx is equal Ax plus b, where b is not equal to 0. We want to show this transformation is not a linear transformation. One of the properties of a linear transformation is T0 should be equal 0. This is if the transformation is linear. So now let us apply this one here and let us find what is T0. So T0 will be equal A0 plus B. We know that A0 is equal 0 plus B. This will give us B. And it is given that B is not equal to 0. So this one is not equal to 0. So the transformation is not linear. Is not linear since T0 is not equal 0. So from here we show that the transformation is not linear. If B is equal to 0, the transformation will be different. But here B is not equal to 0, so that's why we conclude that this one is not linear transformation. In 31, let T be Rn to Rm be a linear transformation, and let V1, V2, V3 be a linearly dependent set in Rn. So we given that this set is linearly dependent set. So that's mean C1 V1 plus C2 V2 plus C3 V3 is equal 0 for C1, C2, C3, not all of them 0. Because it said linearly dependent, that's mean not all these C are 0. So explain why the set TV1, TV2, TV3 is linearly dependent. So we'll do linear transformation for this one. So we'll add T C1 V1 plus C2 V2 plus C3 V3 is equal T0. We want to show that this one also the set is linearly dependent. So we know that TC1 V1 plus C2 V2 plus C3 V3 we can use the properties. So this is C1 TV1 plus C2 TV2 plus C3 TV3, which is equal T0 is equal 0 since the transformation is linear. Now we said here from the beginning C1, C2, C3, not all of them 0. So also here they are the same. So since C1, C2, C3, not all 0, the set should be اللي هي TV1, TV2, TV3 is linearly dependent set. So if you have a set which is linearly dependent and you have a linear transformation, after the transformation, the new set also will be linearly dependent.